Good day everyone, my name is Jose Ballesteros from Team 52 and today we're presenting our project, which focuses on a replication of an existing research study that focuses on how smartphones can be used to detect thumb position during one-handed use. The study by Kunihiro Kato and Kaori Kematsu proposed a method to detect thumb postures above a smartphone screen using acoustic sensing. Their system works by emitting inaudible sound waves from phone speakers. These sound waves reflect off the user's thumb, and the phone analyzes how the signal waves change when it returns. Using this reflected data, the system can classify different thumb positions without needing any additional hardware. In their experiment, they collected data from 10 participants, each performing multiple thumb gestures. They then applied machine learning models such as random forest and support vector machines to classify 12 different thumb postures. The results showed that the system could achieve up to 87% accuracy, especially on devices with acoustic surface technology. Overall, this study demonstrates a powerful idea, enabling more advanced one-handed smartphone interactions using only sounds. The goal of our project was to replicate this original study and understand how accurately we could detect thumb positions. We aim to develop an application that uses sonar data to detect thumb placements on the screen. We also collected data from different screen regions and used machine learning models to predict thumb positions. Ultimately, our objective was to match the original study's results or get as close as possible within a reasonable margin of error. In terms of applications, this technology could be used for gesture-based controls and improving one-handed user interfaces on smartphones. At this point, while replicating the study, we made several adjustments. First, at this moment in time, we have only been able to collect data from 9 participants instead of 10. Second, our participants used a variety of Android phone models, whereas the original study used only 2 specific devices. Another key difference is that our system used only the phone speaker and microphone, while the original study used additional acoustic hardware. Finally, we experimented with 5 machine learning models instead of 4, allowing us to compare more approaches. For data collection, we recruited participants from friends, family, and different classmates. We shared our app through messaging platforms like WhatsApp, class forums, and provided instructions on how to run the experiment. Participants used the app and recorded sonar data locally on their devices and then was transferred to us for analysis. We developed a mobile application specifically for collecting sonar data. The app includes 5 thumb placement areas for both the top and bottom of the screen. Users tap different regions, and the app records the corresponding sonar reflections. As shown on this slide, the interface supports both left-handed and right-handed users, making it more inclusive and flexible. To conclude, our project showed that the original study is feasible to replicate. We expanded on the original work by including a wider range of devices and testing additional machine learning models. At this point in time, we are yet to complete analyzing our findings with our first model, as we have spent time researching these technologies and creating the proper data transfer pipeline that will be used to feed the models and perform the necessary analysis. Once this is in place, working with the different libraries will be much easier. The remainder of the time will be spent refining our models and comparing results against the original project, in order to answer our initial hypothesis of whether we were able to properly achieve a similar result within the original study's margin of error. However, this project demonstrates the potential of using acoustic sensing for improving smartphone interaction in a simple and hardware-free way. Thank you so much, and I hope everyone has a great one.